Hello everyone, I'm Justin and today we are going to talk about random forests. In this module, we are going to learn how to classify categorical data or numerical data on decision trees. Then, we will learn the steps on how to build a decision tree. Finally, we use the decision tree knowledge to build a random forest. Without further ado, let's get started. So, what is a random forest? A random forest is a type of supervised machine learning algorithm where it splits dataset into training set and testing set to predict the outcome of a result. The good news is random forest works well in both the classification and regression problems. And random forest is actually made up from many individual decision trees, which is why we have to learn the concept of decision tree before delving into random forest. So now, it is better to ask, what is a decision tree? Well, a decision tree is a flowchart-like structure in which each branch represents an outcome of the input. This is a simple example of a decision tree classification. Here, we have several apples and oranges and we want to classify them. Here, we split the data by asking if the data is an apple. If yes, then it will be labeled into the yes category. If no, it will be labeled into the no category. And this is how you classify a simple dataset using a decision tree. Now, what we have more than two categories in our classification. Well, decision tree can also do the job for us. In this example, we ask the data again if it is an apple. If yes, all the apples will be labeled into the left-hand branch. If no, it will be labeled into the right-hand branch. And to split our data even further, we ask our apple dataset if it is red in color. And this is how we classify our data if they have more than two categories. Some jargon to be used here. The original data at the top of the decision tree is called the root node. The internal nodes are simply called nodes. And lastly, we have the leaf node, the final categorized data that we want. So, can a decision tree work on regression problems as well? The answer is yes. For numerical data, we will simply split them by asking if the data is more than or less than a threshold value that we set. In this case, if the person is higher than 160 centimeters. Once this all set, let us begin by learning how to build a decision tree for each variables or columns. Here, I have 50 patients with smoking, drinking, and lung cancer records. We want to know if smoking or drinking can cause lung cancer. Let's work on the smoking variable first. For patient number 1, he or she smokes and is diagnosed with lung cancer. So the leaf node at the most left will be 1. The second patient does not smoke but diagnosed with lung cancer. Hence, the leaf node here will be labeled as 1. And repeat this method with all the remaining patients. Hence, we have worked out the decision tree for the smoking variable. To save time, I'll also show you the result of the decision tree made from the drinking variable here. In modern day research, there are many evidence showing that smoking or drinking can indeed trigger lung cancer. But why is our data inaccurate in doing so? Theoretically, a perfect data would have shown that all these circle numbers would to have a maximum value. However, in reality, not all leaf nodes are pure. In other words, not all data are 100% yes or 100% no. So, how do we evaluate these impurities? This leads us to introduce the concept of Gini index or Gini impurity. A Gini impurity is a score that evaluates a certain pureness in each node. The formula for Gini impurity is 1 minus the sum of the probability of yes squared and the sum of the probability of no squared. That is to say, if the Gini impurity is smaller, the node will be purer. Let's calculate the Gini impurity for smoking. In the left node, the Gini impurity will be 1 minus the probability of yes squared minus the probability of no squared. Hence, we found that our left node of the Gini impurity to be 0.495. And we did the same calculation for the right node. And we get the Gini impurity to be 0.444. Once we get the Gini impurities for all the nodes, we can hence calculate the Gini impurity of smoking. Take note here that the total number of patients at the left leaf node is not the same as the total number of patients at the right leaf node. Therefore, to calculate the Gini impurity of smoking, we have to find the weighted average of Gini impurities for all the leaf nodes. After doing some math, we found that the Gini impurity of smoking is 0.474. And we use the same strategy to work out the Gini impurity of drinking. And the value is equal to 0.496. Once all set, we can proceed to build decision tree for our data set. Recall that the smaller the Gini impurity value, the purer the results. Here, the Gini impurity of smoking has a smaller value than drinking. Hence, smoking will be our root nodes. With this dataset, we need to figure out of 29 patients with smoking records, in which 16 of them with lung cancer and 13 of them without lung cancer, how many of them drinks or don't drink but have or don't have lung cancer. And we do the same for the 21 non-smoking patients. Once this is done, we can then evaluate the Gini impurity for each of the leaf nodes. So now, on the left node, the Gini impurity score is 0.481, whereas the right node will have a total Gini impurity score of 0.371. Recall that we did the same calculation for the Gini impurity of smoking on each node. Now we compare the newly found Gini impurity with the previously calculated Gini impurity. Whoever Gini impurity score is lower, that will be our leaf node. In this case, we have the correct decision tree since the newly evaluated Gini scores are lower. But if let's say the Gini impurity score of the previous leaf node is smaller in value, hence we will stop at the leaf node with the lowest impurity score like this. And this is how we made a decision tree. Take note that our sample size is really very small, and the actual decision tree of a real-life problem may look like this. So, to summarize what we have done so far, firstly, we calculate the Gini impurity scores for all the categories. Then, we choose the category with the lowest Gini impurity score as the root node. After that, we work out the remaining nodes. If the node itself has the lowest Gini impurity score, then it is unnecessary to split the nodes further, and hence it becomes the leaf node. And if splitting the data result is an improvement, we pick the splitting with the lowest impurity score. Now you may ask me, Justin, what about numerical data? For example, this data. Can we build a decision tree on it? The answer is yes, by following the few steps. First, sort the numerical data value from the lowest to the highest, or vice versa. Then, we calculate the average height for each adjacent data. After that, we calculate the Gini impurity for each average height. We found that patient with shorter than 163 cm has the lowest Gini impurity score. Hence, this will be the cut-off impurity value when comparing with other categorical or numerical data. Sweet! Now that you have learned how to build a decision tree, let us begin by working on the main topic for today, that is, to build a random forest. Step 1. Create a bootstrapped dataset. A bootstrapped dataset is dataset which has the same size as the original data, and the data sample is randomly selected from the original data. Let us take a look at our original data consisting of only 5 datasets and our bootstrapped dataset. And since all the data samples in the bootstrapped data are randomly selected, you may encounter some duplicated data chosen from the original data, and that is perfectly fine. Step 2. Create a decision tree using a random subset of variables or columns at each step. Here, I will use only 2 variables for each step. Assume that we have randomly chosen drinking and height as the 2 variables for our decision tree. Same as before, we work out the Gini impurity scores. Then we found out that drinking has a smaller impurity score, hence it will be our root node. Then for the remaining 3 variables, we randomly selected 2 variables to be our next nodes. And we repeat this method until we have arrived to all the leaf nodes. Step 3. Repeat step 1 and step 2, that is, to make a new decision tree out from the new bootstrapped data. For illustration purpose, I have worked out another 5 decision trees. And these 6 decision trees are our random forest. Sounds easy to make, but how does it work? To test our random forest model, we take a look at a newly chipped in dataset with no record of lung cancer. Using our random forest, we can try to predict whether or not this patient has lung cancer. So, we take the data and run it into the first decision tree that we made. The first tree predicted that this patient will have lung cancer, whereas the second tree predicted that this patient will not have lung cancer. Once we run the data into all our trees in the random forest, we then check and see which of the option has the more votes. In this case, the yes option received the most votes, and we concluded that this patient has lung cancer. Recall that we created bootstrapped dataset and we allowed duplicate entries in the bootstrapped dataset. What about those data that are not selected into the bootstrapped data? Take note that about 1/3 of the original data will not end up in the bootstrapped data. The left out data set is called out of bag dataset. Actually, we can put our out of bag dataset into good use by testing the accuracy of our random forest. Same thing as previous, we run the out of bag data into the trees of random forest and we check if the result used the same as the original records. And if it is the same, then we will verify the accuracy of our random forest. If the result is not the same, then this accuracy will be the out of bag error. In summary, we have built a random forest. Then we test our random forest model and evaluate its accuracy using the out of bag data. If the out of bag error is significant, we go back to the building model of our random forest and do some adjustment. Remember that we use 2 random variables per step to build our tree. We can actually change the number of variables used at each step to see if our random forest model improves its accuracy.